Okay. Okay. Good morning to everyone. Welcome to our next seminar. I am very honored and to present Claire Donnelly. Claire is a researcher from the Max Planck Institute for Chemical Physics of Solids in Germany. She will share with us the talk entitled Unravelling Three-Dimensional Spin Texture from Bulk to 3D Nanomagnets. Okay, a bit of Claire. Claire did his master in physics at the University of Oxford. Her PhD studies were done at Paul Scherrer Institute and ETH Zurich. In 2017, she was awarded for her work on 3D systems and recognized by a number of prizes, including the APS Richard Green Dissertation Award, the Werner Meyer-Ilse Memorial Award, the ETH Medal, and the SPS Award for Computational Physics. She did a postdoc at the ETH Zurich, and after that, she went to the University of Cambridge as an early career research fellow, okay, at the Cavendish Laboratory. Also, she was awarded with the L'Oreal Prize for Women in Science, and also by the European Magnetism Association as a young scientist award. So since 2021, she is a Lice Miner group leader of Spin 3D at the Max Planck Institute for Chemical Physics of Solids in Dresden. And recently, she was awarded with the IEEE Magnetic Society Early Career Award by the IEEE Magnetic Society. Sorry. So Claire, the audience is yours. You can share your screen and start the presentation whenever you want.
Okay, so thank you very much, Luis. I'll share my screen now.
Yeah.
Do you see?
Yes.
Yes. Okay. Yes. Perfect. Okay. So so I guess with that I'll start, and I'd like to start with a big thank you for the invitation. It's really nice to be able to speak to you today about some of the work we've been doing over the past few years. And also to be able to speak to you over Zoom to the other side of the world, which is still a little bit of a novelty. So we were just speaking beforehand about the fact that you now have snow and we are seeing the first warm days of the spring, so it's quite funny. Okay, so yeah, as mentioned, I am now, let's see, a group leader at the Max Planck Institute for Chemical Physics of Solids in Dresden in Germany. And today I'm going to be speaking to you about our work on three-dimensional magnetic systems. So just a little bit about myself. I mentioned I'm a group leader. My group is called Spin 3D. I'm lucky enough to work with a fantastic group of people in my group and also many collaborators. We're based in the city of Dresden. For those of you who are not familiar with it, it's a really nice city. It's got a beautiful, let's say, old town right on the river. And let's see, while we're not on the river, we're in the institute and we're working mainly on three-dimensional magnetic systems. So I thought I'd first of all start with a quick mention or a quick sort of addressing the question of why are we interested in three-dimensional magnetic systems? And I think in order to answer that question, we need to start about thinking about magnetic systems in general and nanomagnetism. And the fact is that in the, let's say, last few decades, the vast majority of nanomagnetic systems and also micromagnetism has occurred in two-dimensional planar systems, where there's been a huge amount done, let's say, in terms of devices, but also the fundamental physics that can be looked into. But what we are particularly interested in is the idea that when we take magnetic systems from 2 dimensions up to the 3rd dimension, we have a huge increase in the number of possible geometries and also functionalities that become available to us. So, for example, we can think about 3-dimensional topological textures that become possible. We have such as magnetic Hopfions, or let's say skyrmion structures forming 3-dimensional networks. We have the possibility to look at curvature-induced effects such as geometric-induced effects such as curvature-induced anisotropy and Jalaszynski-Maria interaction. And we also, of course, have the opportunity for devices. And by that, what we mean is when we go to the 3rd dimension, we have the possibility for increases both in density as we see in this well-known example of the racetrack memory proposed by Stuart Barkin. But also, let's say, increases in interconnectivity, which is of course important for future, let's say, alternative types of computing devices. Okay, so if we first of all think a little bit about the idea of topological textures, we can think through each of these three ideas. The question first of all is, why are we wanting to go to three-dimensional? What does it mean going to three-dimensional topological textures? Well, with this, the key sort of idea of topology, which we can remind ourselves of, is the idea that this is a GIF, is with topology, if two structures are topologically equivalent, is the idea, just like the coffee cup and the mug, that they can be smoothly transformed one into the other. So what essentially that means is that we have our coffee cup or our teacup that's equivalent to our donut, but it's not equivalent to one of the nice discoveries I've made in a German bakery recently, which is the donut pretzel, which of course has more holes and is, let's say, topologically non-equivalent. Now, in terms of dimensionality, in the magnetization, we can therefore have different types of topological structures. We can first of all have two-dimensional spins in 2D, where we would have vortices, let's say, that are defined by the winding number, which is then thought of in the two-dimensional plane. We can then think about three-dimensional spins, so give our spin or our vector field a three-dimensional aspect, but again think in two-dimensional planes. And this takes us to the skyrmion number, where you would integrate the skyrmion number over a two-dimensional area. And then we can go up in terms of dimensionality to three-dimensional spins in 3D space. And this takes us to the Hopfion, or the Hopf index, which is a structure of really recent interest. Essentially, it's the equivalent of a knot in the magnetization, really, in 3D. There's a lot of interest in the last few years about what this, or whether these could actually be realized and potentially used for future applications. So when we think first of all about, let's say, what happens when we go to 3 dimensions, we can think first of all about the idea of skyrmion structures. So I think many of you will be very familiar with this. Skyrmion textures are very well established in magnetic thin film devices, but also in, let's say, bulk Kairos systems. They've even been proposed for possible devices, such as racetrack devices or even neuromorphic computing devices. But when we think about the three-dimensionality effect, so when we take these essentially structures that are defined by their topological index calculated in a plane, but we take them to bulk-like systems, we have the possibility for non-trivial transformations of the topology in 3 dimensions. So these skyrmions are typically thought of as tube-like structures that propagate through the thickness of a system. But within the thickness of a system, within the bulk, you can have the presence of Bloch point singularities that allow for a transformation of the topology. And this shows, let's say, it gives an example of why going to 3 dimensions is so motivating. Now we can go, let's say, up to the next dimension and think simply about this Hopfion structure. And as I mentioned, it's been of growing interest in the last few years, really since, let's say, 2017, 2018, people have started talking about this. And it's really the equivalent of a magnetic knot that a number of theoretical works or simulations have predicted to be stable in the last few years. Now, what's really exciting is that in the last, let's say, couple of years, we've had the first reports of possible observations of these Hopfions, both in thin film heterostructures, but also in chiromagnets. And I think this is something that in the next few years, we can really look forward to, so let's say, observing in 3 dimensions and manipulating, let's say, as we go forward. Now, the last kind of thing that I want to, or let's say topic that I want to mention as part of the introduction into 3-dimensional magnetism is coming back to this idea, not just of textures that occur within the magnetization vector field, but also of this idea of the geometric tuning of magnetic properties. And with that, we can think a little bit about this idea of chirality. So many of us will be familiar with this idea of the Jelizinski-Maria interaction that leads to exotic chiral states. So in, let's say, in well-known kind of 2D systems or crystals, we have fermions, we have the possibility for spin spirals. But up until now, in order to get chirality into a system, you've pretty much needed either very specific materials which intrinsically break inversion symmetry and are intrinsically chiral, let's say in terms of their crystal structure, or else you need perfect interfacial effects. So you need very high quality interfaces. Now, there's an alternative way that we can achieve chirality in our system, and that is by the breaking of symmetry via the geometry. Now, you can introduce that via curvature. For example, in thin films, you can see that introducing curvature leads to a starting of a chirality of a Landau pattern, whereas on, let's say, nanotube-like structures, you get a breaking of the symmetry, leading to magnetochiral sort of non-reciprocity and domain wall motion. But we can also think about patterning chiral geometries directly. So really patterning chiral helical structures that can lead to then intrinsic chirality in a system. So as you can see, or hopefully what I've spoken about in the last few minutes, you're also motivated by the idea of three-dimensional magnetic systems and kind of the exciting next steps we can take beyond two-dimensional nanomagnetism. And this is the main part of my group and my work over the last few years has been working in this direction. Now, I'm an experimental researcher, or experimental physicist, so we want to look at these three-dimensional magnetic systems experimentally. And for that, we need a number of tools. So first of all, we need to be able to visualize these three-dimensional textures. So we need new imaging techniques. Secondly, we need to be able to fabricate them. So essentially, we need a 3D printer with magnetic materials. And lastly, we need to be able to understand them. And this comes back to this idea of understanding the types of potentially topological textures that we can expect in 3 dimensions. And I'll be touching on each of these things during the course of my talk. Okay, so today, let's see, in my talk, I've kind of split it up into 2 main areas that was reflected in the title. The first part that I'm going to be speaking about is the idea of 3-dimensional magnetic systems in bulk-like configurations. So what do we mean by bulk? We mean in the idea or in systems where we are not confined, where the magnetization is not confined. And by this, for example, we can think about macrosystems, where we have observed Bloch point singularities, magnetic vortex rings, and even toron-like structures. In the second part of my talk, I'll speak about more confined systems, so patterned 3-dimensional magnetic nanostructures. In particular, I'll focus on this idea of chiral systems, where we have the possibility to introduce chirality in this way, and also observe, let's say, resulting chirality in our magnetic systems as well. Okay, but let's start off with our bulk-like systems. So I mentioned before, in order to look at or visualize three-dimensional systems, we need new imaging techniques. And this is particularly important in bulk-like systems, where essentially we need to be able to see within the bulk of a material. And for this, over the last few years, we've developed magnetic tomography, which is a 3-dimensional imaging technique equivalent to the CT scan at the hospital, where we have 3 basic ingredients. We get 2-dimensional projections of the magnetization. We measure these at many different orientations, which allows us to probe all 3 components of our vector field. And then we use a reconstruction algorithm to reconstruct our vector field from this data. And when thinking about, let's say, what technique we can use, there are different probes that we have our choice of. We have, for example, the possibility to measure with electrons, where you measure B. Typically, you measure very high spatial resolution, but you're limited to thin systems. You also have the possibility of measuring with neutrons, again, measuring the magnetic induction. This time we're kind of on the opposite extreme, where we're measuring thick systems, so up to millimeters or even centimeters, but with relatively poor resolution of let's say tens, hundreds of micrometers. And then we also have X-rays. And I like to think that X-rays kind of build the bridge, or they get the best of both worlds. So we can use higher energy X-rays to target thicker systems, to look really into bulky micrometer-sized systems, but retaining the nanoscale spatial resolution that we need in order to resolve magnetic textures. And it's for this reason that we focus on X-rays in our system. So for X-rays, of course, we go to the synchrotron. We make use of a lot of synchrotron radiation in our work, in the work of my group. It involves quite a lot of traveling around. So we've been to a number of different synchrotrons in Europe over the last, let's say, year or so of the group. We're going to a few more, and I've just come back from one last week as well. So essentially, yeah, this is a big part of the work that we do, but we enjoy it and we have quite a lot of fun. So what I can do is I can first of all, let's say, introduce you into this idea of magnetic tomography with the first demonstration of the, let's say, that we have performed with this technique. And for that, we looked at a gadolinium cobalt pillar. It's a ferrimagnet that we can model as a soft ferromagnet. And when we take magnetic projections with X-ray magnetic circular dichroism, we are taking a projection of the magnetization through the pillar. So what we can see is that in this XMCD image down here, we have a projection of our magnetization vector field. We have dark regions and bright regions where the magnetization is pointing towards or away from the screen. Now essentially we measure hundreds, I think we measured about 5 or maybe 1,000 projections for this data set. And by using the reconstruction algorithm, we can reconstruct the internal magnetization, as you see here in this video. So this is a static configuration, but we're just showing it dynamically by moving the slice through the system. And we can see that, as expected for this material, our magnetization is relatively smoothly varying, but it has a number of twists and turns inside that are particularly intriguing. So we can look in a little bit more detail. First of all, thinking about the different sort of levels of topology in our system, we can first of all think about two-dimensional textures that we observe. So we plot our two-dimensional vector field, and we see immediately, this is a horizontal slice through the structure, we see a number of very familiar looking structures. So we see vortices where the magnetization circulates around a certain point. And we see anti-vortices where we have the, let's say, opposite winding number and a saddle, more saddle-like structure. Now, of course, we have a three-dimensional data set, so this allows us to take, let's say, our dimensionality up a notch to go to really look at what the three-dimensional topology of these textures is. And in order to have a look in this direction, what we do is we follow the, let's say, the vortex core of the central vortex that we saw in the previous slice, as it propagates through the height of the structure. And what I'm showing you here is, let's say, okay, we'll talk through it step by step. We have, let's say, a cylinder, which is just a cutout of our data, and the color is representing the vertical component of the magnetization. So we have, we have our core basically passing from one side. Let's say I've a domain where the magnetization is pointing up on the left-hand side to the domain where the magnetization was pointing down on the right-hand side. Now this crossing of this domain wall is associated with a reversal of the polarization of our vortex, meaning that we have the presence of these Bloch point singularities within our data. Now, indeed, when we plot the magnetization in the vicinity of these crossover points, we see first of all a circulating Bloch point where we have a vortex in the plane and a kind of a divergence of the magnetization up above and below. And at the other crossover point, we see a more twisted structure, which corresponds to an anti-Bloch point. And I think this was a really exciting sort of moment when we saw this, because it was the first time that we've been able to really observe such defects in the magnetization in 3 dimensions. And it gives us an idea of the power of, let's say, these 3D imaging techniques and the kind of new physics that we can see with this. But as you can imagine, so we're very excited to see these Bloch point textures. But as you can imagine, with these data sets, we have certain challenges that come with this huge amount of data. In particular, we have millions upon millions of pixels, each with 3 components of the magnetization. And as a result, it can be quite challenging to, let's say, wade through all of this data and pick out the relevant textures. So in order to do so, what we've recently done is, let's say, built up some capabilities to actually identify relevant objects and understand them that occur in 3D. In particular, what we do is we calculate the so-called magnetic vorticity vector, which is essentially a quantity that is related to the topology of our vector field. It's related to the flux of the skyrmion number density. Now we can see what this means for some sort of basic vortex structures first of all. If we consider vortices, with a core pointing up or down, our vorticity is pointing parallel to the core. Whereas for anti-vortices with the opposite topology, the vorticity points anti-parallel to the core, reflecting again that this quantity is related to the topology of our system. Okay, so what we can do is we can then go on to our data, and we can first of all simply plot regions of high vorticity in our structure, which reveals a network of essentially cores of topological textures occurring in 3 dimensions. So you can see that we have, let's say, extended, lines of vortex cores, but also so-called sort of loop-like structures occurring as well. We can go a step further and we can plot, so we're looking potentially for these topological defects. In order to find those, we can plot regions where we have abrupt changes in the topology of the magnetization by plotting regions of divergent vorticity. And in this way, we are able to observe more than 50 Bloch point singularities within the structure. Interestingly enough, we see an equal number of positive and negative, so Bloch points and anti-Bloch points, indicating that we really have very likely the formation of pairs of these defects occurring within the bulk of the system. And when we plot, of course, the vicinity of these Bloch points, we see, let's say, in the magnetization, what we saw before, so this circulating Bloch point or this anti-Bloch point. But in the vorticity, we either have a sink or a source of our essentially topological index. And if anyone's interested in this, I would really point you to this other paper by Aurelio Hierro Rodriguez, which is also, let's say, working along the same lines. Okay, so we've seen so far that with the vorticity vector, we can identify relevant structures in our data, which is hugely helpful. But we can also use this to help, let's say, gain a better understanding of certain textures that we see within our data. And in particular, one such texture that we were particularly intrigued by are these loops of vortex and anti-vortex cores that we observe within the magnetization. Now, what was quite interesting was that we saw a number of these loops. They all had roughly the same diameter, so between 300 and 400 nanometers. But it wasn't until we plotted the magnetic vorticity vector that we realized what these were. So you can see the vorticity vector is circulating around the loop in a circle. And what this means is that these are magnetic vortex rings that were predicted in the 1990s by Nigel Cooper from Cambridge, but had not been directly on magnetization up until this point. Now, what's pretty exciting is that these vortex rings are pretty much directly analogous to vortex rings that are seen in other systems, such as bubble rings or smoke rings in hydrodynamics. And this gives us an idea potentially of, let's say, the interesting dynamics we might be able to see in the future. But for now, what we were interested in was understanding why these loops are stable, why they are occurring in our relatively simple, or one may say like boring material. And for this, of course, the next thing that we were interested in was working out whether the topology was the root cause of this. So in order to work out whether the topology was helping out with this stability, we took inspiration from our colleagues working on magnetic Hopf fields, and where they plot pre-images, so essentially isosurfaces of the magnetization corresponding to different directions of the vector field. And if these isosurfaces link, then you have a non-zero Hopf index and you have a Hopfion. But unfortunately, when we applied this analysis to our own data, we had a number of these loops, but they did not link, meaning that this is not a Hopfion, it's actually a topologically trivial state. As I said before, though, it was very intriguing because we saw a number of these structures. They all had relatively simple sizes. And it turned out when we were doing some analytical modelling, it's actually the magnetostatic interaction that appears to be key to stabilizing these textures. So we have a relatively simple balance of exchange and magnetostatics. And this is something that I think will be important for us to bear in mind as we go to potentially, let's say, Cairo systems in the future, that the magnetostatics can play a very important role in stabilizing certain textures. As well as seeing these, let's say, topologically trivial vortex rings, we also saw some more interesting textures in our magnetic configuration. In particular, some vortex rings that contained these Bloch point singularities, so where the magnetic vorticity vector actually changes direction. And we have a pair of a Bloch point and an anti-Bloch point that have formed within the vortex and are existing on this ring. Now, when we plot our pre-images, like we would for the Hopfion structure, we realize that these pre-images essentially create a kind of onion-like texture. What this allows us to identify these rings as are torons. Now, these torons have been observed in other types of systems, such as liquid crystals. And what's really exciting here is that they're often observed alongside topologically non-trivial Hopfions. And even more interesting is the fact that certain micromagnetic simulations of Hopfion structures in the last few years have predicted, again, that these torons will be stable alongside Hopfions, but that they may be, let's say, form a part or play a role in the, let's say, either the, the formation or the annihilation of Hopfion structures dynamically as well. So this, although we did not observe our Hopfions, we saw a number of structures that, let's say, give us some hope that sometime in the near future we might be able to do so in 3D. Now, as I mentioned before, let's say, seeing all of these interesting textures gives us a lot to think about statically, but dynamically, this is also opening up a really interesting direction when it comes to thinking about the behavior of magnetization dynamics or magnetic structures in 3 dimensions. Now, when we come back to our tools, we need to think about whether we can measure this. And first of all, when we think about the techniques that we have available to us, we have tomography, which is a non-destructive 3D imaging technique. We see already that it works very nicely. But the question, of course, is can we apply this to dynamics? Can we apply this to a sample that we are exciting structures? Typically, we need electrical contacts for this. And then typically we would use a flatter surface. Now the problem happens essentially when you're rotating your flat surface. At some point you're going to block your beam. This is the so-called missing wedge, and you'll lose information. Now an alternative way of measuring instead is the so-called laminography geometry, where instead of having your rotation axis perpendicular to your x-rays, my left hand is my x-rays, we actually rotate our rotation axis, let's say, towards the x-rays, and we rotate like this. And what this means actually is it's possible to measure extended samples without this blocking of the beam. Now, this is something that we've also applied to 3-dimensional magnetic imaging. And luckily for us, an added advantage of being able to measure extended structures is that with the laminography geometry, we probe all 3 components of our magnetization vector field, meaning that this actually ends up being a much simpler experiment in the end. Now, we have our 3-dimensional imaging technique then. Essentially, we combine this with pump probe imaging, making use of the temporal structure of the synchrotron, where we have our X-rays coming in picoseconds, so 70 picosecond wide pulses. And essentially, by measuring 3-dimensional data sets for different time delays, we can get our 4-dimensional information. Now, the structure that we were looking at here was a 1.2 micrometer thick gadolinium cobalt disk. We can first of all look at its 3-dimensional magnetic configuration. And we see that we have a change in the anisotropy through the height of our structure. So in the top part, we have a relatively high anisotropy. We have therefore a single domain structure. And in the bottom part, we have a relatively low anisotropy and we have a double vortex state. Now, this double vortex state allows us to directly look at the magnetization dynamics of these vortex textures. And in particular, when we map this, let's say this slice dynamically, we see here, what I'm showing you here is a difference image where we have this dark line gyrating from one side to the other of this white reference line. So we're able to observe the motion at 500 megahertz of these vortex-like structures buried within the material. Now we can track the propagation of these vortices. We can determine that they're moving at 200 meters per second. We can track them with very high accuracy. And what this demonstrates is that it is possible really to track and map the dynamics of topological textures within a three-dimensional system. Now, of course, as well as tracking textures, what we can also do is we can look at the rotation of the magnetization. So, for example, coherent rotation or the propagation of spin waves in a system. And in order to do this, what we do is we perform Fourier analysis of our four-dimensional data. We can pick out the frequency at which we want to visualize our dynamics. What I'm showing you here is the red, let's say a video where our red regions represent regions where we have a high magnitude of our magnetization dynamics. And what you can see as a result is that we're able to then map this through the three-dimensional structure, and we see a very inhomogeneous let's say structure of the dynamics, where the dynamics are closely correlated with the textures and let's say magnetic configuration of our system, as one would expect. Now, this is, I think, very exciting for going on to look at these complex three-dimensional topological textures in the future, and it's something that we've been working on that maybe in a few years I'll be able to tell you a little bit more about. Now, just very briefly before I go on to the second part of my talk, I just wanted to mention that for those who are interested in these techniques, that this three-dimensional dynamic imaging, we've now also implemented this with soft X-ray scanning transmission X-ray microscopy. So previously I was talking about hard X-ray imaging, where we look at very bulk-like systems. Now, what this allows us to do is look at more nanostructure-like materials. For example, mapping out thin film systems that host, for example, target skyrmions. But what is particularly powerful about this part of the technique is that we can harness time-resolved scanning transmission X-ray microscopy. And what this allows us to do essentially is to tune the excitation frequency. So we're not limited to the excitation frequency of the synchrotron, as we were in the previous case, so to 500 megahertz. But because we're now working with a diode, we can, let's say, look at, tune or excite the system at many different frequencies to be able to look at resonant dynamics within our system. You can see here an example where we had an anisotropic Landau pattern. We were able to visualize the three-dimensional dynamics of our vortex core at, let's say, 300 megahertz or so, but also by exciting a higher frequency, we were able to look at the excitation of the domain walls themselves. Okay, so so far I've spoken to you about, let's say, our imaging capabilities and what this has allowed us to see in terms of three-dimensional textures and topological textures in more bulk-like systems. But in the last, let's say, 10-15 minutes or so, what I want to speak to you about is the idea of going to patterned three-dimensional nanostructures, and specifically looking at coupled chiral systems, where you can see we've been investigating different types of double helix, cobalt or magnetic double helices. Now, as I mentioned earlier, in order to experimentally investigate three-dimensional magnetic nanostructures, we need a 3D printing technique. And for this, I was lucky enough during my time in Cambridge to work with Amalio Fernandez Pacheco and his student Luca, who have developed such a technique over the last few years. So it's based on the idea of focused electron beam induced deposition, where one has a scanning electron microscope. You inject gas into the chamber and you locally deposit the material with the scanning electron beam. Now, this can be combined with different types of materials. So the standard ones are normally platinum or tungsten, but more recently there's been, or let's say in the last 10, 15 years, there's also been the development of cobalt-based focused electron beam induced deposition, or FEBID as we call it, allowing us to directly write magnetic material. Now, where Amalio and Luca have made huge kind of breakthrough is in the development of 3D nanofabrication capabilities. So combining this FEBID with the idea that we can design three-dimensional geometries in a CAD software, such as you would see here, combining this three-dimensional geometry with a growth model and is essentially outputting a set of instructions for the microscope, you can now realize such three-dimensional geometries on the nanoscale made of functional materials. And as you can imagine, this has been a bit of a game changer for magnetic nanostructures, because now we have the possibility to really pattern arbitrary geometries out of, let's say, it's amorphous or nanocrystalline cobalt, so a relatively soft isotropic magnetic material. And what it sort of opens the door to is the introduction of curvature, as we spoke about before. This allows us to look at chiral effects, for example, but also, for example, topological objects. And these are two examples that Luca, during his PhD, went and fabricated very successfully to demonstrate really the capabilities of this new nanofabrication technique. You can see here that, let's say, we now have what we believe is likely the smallest Mobius strip that, or at least at that time, was realized, magnetic Mobius strip. Okay, so that takes me then to the next, or this last part of my talk, which is now using this nanofabrication capability to pattern geometric chirality effects. And in particular, we're going to be looking at two types of chiral magnetic systems. First of all, overlapping, so exchange coupled magnetic double helices, where we really have let's say, a continuation of the material in between the two structures. And secondly, separated, so dipolar coupled systems. So if we start off with our exchange coupled double helices, we can fabricate these with FEBID. And what is very nice again about this three-dimensional nanofabrication technique is that, as you can see in this structure, we're not limited to just one chirality, but we can actually pattern both chiralities, so both right-handed and left-handed structures in the same nanostructure. And this work was, let's say, mainly led by Dedalo San Hernandez, who was a PhD student in Cambridge, and of course by Amalio was also there as well. Now, when we look with X-rays at this structure, so we go back to our X-ray microscopy, we can see that the magnetic nanostructure, the double helix, is forming, when we compare with simulations, an anti-parallel state. So essentially, one helix is pointing up and the other one is pointing down. Now, what this means is that when we consider what's happening in between, in this overlapping region of the double helices, we have, due to the chiral structure, a chiral domain wall forming. So essentially, the chiral geometry leads to the formation of this chiral spin spiral domain wall running through the center of our geometric structure. Now, as well as, let's say, this is only happening in one part of the chiral system, but as we mentioned before, we of course have the quite unique possibility to look at the join, or the threshold at which the two chiralities meet. And this is relatively similar, let's say, to what you see in nature, for example, these tendril perversions, or for those who remember old-fashioned telephone wires as well, would also host these kind of tendril perversions, or chiral defects in their systems. So now we've patterned this structure from magnetic material. The question is, what happens in terms of the magnetization vector field at this join? And in order to work this out, we went with the X-rays again and visualized the magnetic configuration, or by comparing our XMCD contrast as a function of angle. And essentially what we see is that when we look at this region, which consists of this meeting of the two chiralities, we see that with angle, it's evolving from a point to sort of a bright on top and dark on the bottom. And this is relatively reminiscent of the magnetic contrast you would expect from a vortex texture, where you have in the outer plane geometry the sensitivity to the core of the vortex, and then the in-plane geometry sensitivity to the domains on either side. And indeed, when we perform magnetic simulations, we see that at this join of the two chiralities of these two chiral domain walls, we get this topological defect, which is in this case a magnetic vortex, indicating that via this sort of patterning of chirality, we can achieve relatively complicated or complex magnetic textures and pattern them exactly where we want them to be. Okay, so very last sort of 5 minutes or so of my talk, I'll speak about one last point, which is again double helices, but this time what we're talking about are separated double helices, which are not coupled via the exchange interaction, but rather via the dipolar coupling, so magnetostatic coupling, because they're separated by space. Now, again, with this, in order to fabricate these structures, we go to focused electron beam induced deposition again. As you can see here, we're able to fabricate structures where actually the diameter of a nanowire is about 70 nanometers or so. But what is very nice is that the actual separation of the nanowires, so the separation of the two helices, can be far below that due to the sort of accuracy of the patterning. And indeed, we can get separations of 20 nanometers or so, leading to very strong magnetostatic coupling between the two helices. Now, again, in order to look at the magnetic configuration of this structure, we go to, again, to the synchrotron, to X-ray magnetic circular dichroism. And just like we saw in the exchange coupled system, actually the as-grown state, well, in this case, we can see that the XMCD is black in one helix and white in the other. This is because we are sensitive to the component of the magnetization parallel to the long axis of the helix in this geometry. We essentially see that the two helices again are pointing in opposite directions. Now this is the ground state, essentially because it is closing the magnetic flux, yeah, this is how the helices generally grow as they are grown. But what is particularly interesting here is that by applying a strong magnetic field perpendicular to the long axis of the helix, we can actually stabilize an array or a periodic array of magnetic domain walls whose position is defined by the geometry, so essentially by the pitch of the helix. And now the question comes, what effect does this three-dimensional geometry have on the textures or on the behavior of these domain walls? So in order to answer this, we then go again to our three-dimensional imaging techniques, and we are able to visualize the magnetic configuration within our magnetic double helix. Now you can see here, it's looking a bit noisier than the other data that I showed you, let's say earlier in the talk. This is because we're really working at the limits of the spatial resolution of the technique. So we're really looking at very small textures. But we see nevertheless that if we compare the reconstruction to the direction of the magnetic field that was applied, we have the domains are generally pointing up, as one would expect. But interestingly, the domain walls themselves are pointing in the opposite direction. Now, this was quite surprising in a way. So we would have expected, if we consider, let's say, micro or just curvature effects, we would have expected the magnetic domain walls to point in the direction of the magnetic field. However, when we apply micromagnetic simulations, which are performed in collaboration with Klaas Abert and Dieter Suess, we see in fact that we are able to reproduce this configuration. And indeed, if you had managed to see during the video, which I played a couple of times, we actually have two different states during this evolution. We start off from the saturated state, and it first relaxes into the curvature preferred state, where the magnetic domain walls point in the direction that the field was applied. But the next transition occurs due to the magnetostatic coupling between the helices. Essentially, the domain walls then reverse in order to close the flux, in order to minimize their magnetostatic coupling. And what that leads to is a very strongly bound pair of magnetic domain walls that we've called the so-called locked domain wall state. Now, where this gets quite interesting is where we consider what's happening in terms of the magnetostatics. So far we've seen that the three-dimensional, so that the magnetic field or the magnetic stray field, the magnetic magnetostatics have strongly influenced the magnetization configuration. But the next question is, what's actually happening? How is the three-dimensional geometry changing the magnetostatics and changing our magnetic induction? So in order to see this, we perform micromagnetic simulations and we visualize the stray field surrounding these locked domain walls. And the first thing that we notice is that due to the twisting of the helix, we actually break the symmetry in the sense that on one side of the helix we have domains generally pointing down. This leads to a tilting of the induction in the direction of the domains and a flux channeling. And on the other side of the helix it's pointing up, so we have generally pointing up and pointing down on both sides of the helix. But what we can then see is when we look in the plane perpendicular to the domain wall, we actually observe particular textures occurring in the magnetic induction. So in particular, what we can see is essentially due to the chirality of the helix, we have effective vortices occurring due to the magnetization, which you can see here. So forming from these domains. But in between these vortices at these domain walls, we actually see anti-vortex structures occurring in the magnetic induction. And the way that we understand this is, we can think of it analogous to cross-tie walls that are observed in micromagnetics or in two-dimensional planar permalloy structures, where you would have, let's say, a magnetic domain wall formed of helices, vortices of the same circulation and polarization. And in between these vortices, you need to have a crossing of the magnetization, which takes the form of an anti-vortex in the magnetization. So essentially what's happening here is that due to the chirality of our helix, we have effective vortices of the same chirality forming, and in between we then have this crossing that takes place in the magnetic induction, so forming textures, topological textures in our magnetic induction. And this is pretty, I think this is pretty exciting from the point of view not just of the fundamentals, but also from the potential of patterning nanoscale textures in magnetic fields, and potentially, let's say, there could be some view towards potential applications in this direction as well. Okay, so that takes me pretty much to the end of my talk, but before I end, I want to say a huge thank you to all of those who I've had the pleasure of working with over the years. I've really been very, very lucky to work with a great group of people, both in Switzerland, let's say Laura Heidemann and her group, who I did my PhD with, the Swiss Light Source, who I've had great collaborations with, now the group of Amalio Fernandez Pacheco, with whom I was working when I was in Cambridge, those in Vienna, and now as well, of course, to my group in Dresden. We're having a lot of fun as well. And to conclude, I've told you a little bit about, on the topic of three-dimensional magnetic systems, how we've been building up this toolbox for being able to visualize or being able to study them experimentally and understand what's going on. And I've spoken to you about two main areas. So we've seen textures in the bulk, and we've looked at patterned magnetic nanostructures. And I think in the next few years, it's pretty exciting. There's a lot to be looking forward to, but two main things that I'm hoping to see more of in the next few years is looking at these higher order topological textures, not only just visualizing them, but potentially controlling them. And of course, using our 3D geometries to control and or access and control also complex configurations. So I think with that, I'm maybe a couple of minutes over, so sorry for that. But I'd be very happy to answer any questions, and I'm again very thankful for the chance to chat to you all today.
Thank you very much, Claire, for your amazing talk. I would like to open the session to questions. I have a few questions actually because I really like your talk. But if anyone wants to start, okay. If not, I can go ahead. So I'm very intrigued for the pattern nanostructure. I suppose you have a limitations of the type of materials you can study because you show in slide 28 or 29, I think, that for example, this helix that you prepare has I don't know 200 nanometers, and when you expose that to air, for example, in some conventional ferromagnetic, you won't have a real magnetic structure due to oxidation or passivation, something like that. I suppose you need to do your structure chemically stable to pass from one experiment to the other one. Is that correct?
So okay, so the question is whether the structures are stable or
Yeah.
if we have to okay. You're very right in that sense. The one of the challenges, or I guess one of the strengths but also weaknesses of this technique is that we do not directly like pattern or deposit pure materials. So
Yeah.
we're depositing a kind of carbon, in this case cobalt alloy, and depending on the deposition parameters, you'll have a higher content or higher cobalt content or a lower cobalt content. And essentially what so you need to have, let's say, a high enough maybe voltage or current to get high enough cobalt content that you can have magnetic properties. What we actually do in this case is we do some post what it also means is that this structures are relatively bendy, so they're not always the most stable. What we have been doing is we've been performing some post-processing in the form of annealing, which it has actually two benefits. It forms from an amorphous carbon cobalt alloy, it forms a more nanocrystalline, let's say harder structure, but it also involves kind of the expulsion of carbon to form a carbon shell surrounding the structure. And this actually has the effect of protecting the structure from oxidation. So we actually see that they're very robust once they've been grown, but especially once they've been annealed, they're very robust to oxidation. We don't need to worry about that so much.
Okay. Okay.
Yeah.
And continue with the same topic. So I suppose you start with the simulation of your structures before the preparation, right? And then you do the reconstruction to see if the simulation I know it's right. I am asking this because for me, but I don't have the intuition to propose I don't know a Mobius stripe to how is the monetization
Yeah.
in that case, for example?
Yeah. So I think it's funny actually. So it actually happened both ways. We one of the challenges I think with this types of systems is that when you go to 3D nanostructures or 3D shapes, you kind of have infinite possibilities, right? And then it comes to now this question of what makes sense to in which direction should we go, but it's in what do we expect actually from the magnetic properties and really tuning the magnetic properties. And actually if the story first of all started with these exchange coupled systems. So we spent quite an intense beam time together getting these first results that I showed you here. So let's say looking at the anti-parallel state, thinking about this influence of the chiralities and everything. And in the end, we did the simulations, and it actually all made sense from what we had kind of worked out in terms of the systems. What was quite unusual, I think, was I mean, quite often we are more sort of, we observe interesting things and try to understand them afterwards, as it often is in science. What was quite surprising for us was that in the case of the separated structures, coming from this exchange couple structures, we had been thinking, okay, we probably have this domain wall and everything. We then went on and were thinking about these separated structures where we have the magnetostatic coupling.
Mhm.
And there we were actually thinking, okay, if we have the right structures, maybe we could have this, this coupling of the domain walls, we could have this reversing and all of this. And actually it worked out in the experiments as we expect. I mean, then of course we learned a lot more with more simulations, but it's surprising actually. What I find quite surprising, or let's say this at the end of this sort of tangent, is in these systems, the geometry is really the dominant effect. So I think this is where we're very, very lucky with this
Yeah.
technique. Because it's nanocrystalline and because of the way that the cobalt, nanocrystalline cobalt essentially behaves a bit like permalloy, we're really in the regime where the geometry is really dominating.
Mhm.
And it then starts to become possible to kind of build up an intuition as to what we would expect from this influence of curvature and chirality and magnetostatics in the systems. So we're kind of building up a sort of intuition here, and we're lucky that we have this great collaboration with Klaas Abert and Dieter Suess in Vienna, where we can perform finite element simulations, so
Mhm.
micromagnetic simulations, and we generally are able to, let's see, to reproduce our
Okay,
experimental results.
nice. And from my side, I have one more question. I would like about the gadolinium cobalt disk. So can you change the temperature and study, I don't know, domain wall motion with temperature, or probably observe compensation magnetization effects on the structure, magnetic structure?
Yeah, so this is something that we haven't done. I can stop sharing my screen maybe. This is something that we haven't done yet, but it's something that we're definitely interested in. So the answer would be, in theory, yes. The only challenge that we really have at the moment is the time that it takes to measure these data sets.
Yeah.
So to put it a little bit into perspective, for each of those time slices, I think we measured eight time steps for those videos. Each of those took about 14, 15 hours. And so combining with all of the setup and everything, we essentially needed more time than a standard 1 week of beam time. And then if we were to then change the field, no, change the temperature, you
Oh, I
can
see.
imagine then
Yeah, yeah, yeah.
we're running into months of beam time.
Yeah.
But I think this is where we have a lot of exciting possibilities. So at the moment, we were always measuring, like with the aluminium cobalt, we were always measuring on the C-site beam and the Swiss light source. And for example, we have where the SLS is shutting down in October for its upgrade, but we have, let's say, the upgrades of the third generation synchrotrons, and we have the fourth generation synchrotrons coming online as well. So like Max 4 in Sweden and Sirius in Brazil. And I think this is where we will see a huge improvement, because we have orders of magnitude, potentially orders of magnitude more coherent flux. And in our case, where we're really limited by flux, this is directly going to translate into either higher resolution or faster measurements. And so what I hope is in the next, I don't know, the next 5, well, maybe even sooner, 3,
Mm.
4, 5 years, we'll be able to really start to do these types of,
Okay.
these experiments where we can vary different parameters and then look at the effect on the three-dimensional textures. Yeah. So
Okay.
fingers crossed. Let's see.
Nice. And so one last more technical question. You mentioned for the reconstruction, you need to detect each component of the magnetization in the XMCD experiment, right? So you do that, I suppose,
Yeah.
is you can do it simultaneously, right? Yeah. Or do you need,
So
yeah.
okay, this is, yeah. So in the in like XMCD, as you know, so you have your X-rays coming in and you're probing the magnetization parallel or anti-parallel to the X-rays, so the component parallel, which means that if you have a tomographic rotation axis, at standard tomography, your rotation axis is perpendicular. You rotate just around 1. And what that means is that you are essentially probing the magnetization in a plane, but you're not probing this component parallel to the rotation axis. So we essentially, in tomography, we need to measure multiple tomographic data sets, so at least 2. But in laminography, because we are rotating around here, we actually get it's almost like the X-rays are coming in a cone, and then we are probing all 3 components of the magnetization in that way. Yeah.
Okay.
But no, we need more data than the standard tomography, essentially.
Yeah. Okay. Nice. That's all from my side. Is there any other question? Okay. If not, thank you, Claire, for this amazing talk. I really enjoy knowing about the all different 3D structure that you study. You're welcome to share your work with us whenever you want. With that, I would like to end the seminar of this week and see you again in 15 days. Thank you. Thank you again, Claire.
Bye-bye. See you later.
Bye.